Hi, my name is Jake Bergquist, and I'm here today to talk to you about a novel experimental preparation to assess electrocardiographic imaging. I probably don't need to stress to this crowd that electrocardiographic imaging has been emerging as a way to non-invasively diagnose and potentially treat various cardiac dysfunctions.
ECGI leverages the physical principles that dictate how cardiac electrical activity can be seen from the torso surface, and then uses torso surface recordings to reconstruct this electrical activity at the heart. Despite ECGI's clinical success, validation studies have been plagued by a myriad of controlled and uncontrolled error, such as errors in the geometric model, heterogeneities in conductivity, incomplete sampling of the cardiac source, noisy signals, and a myriad of other sources. There's clearly a need for an experimental validation platform that controls as many of these errors as possible and allows for further development and validation of ECGI techniques. To address this need, we have developed a unique experimental setup with several sources of error in mind. To control for conductivity, we have developed a Langendorf torso tank experimental preparation. The torso tank is filled with a conductive medium that has a known conductivity, removing any errors associated with inaccurate measurement or assumption of conductivity values in an inhomogeneous torso. To control for cardiac sampling, we've developed several novel recording arrays. This includes the 192 electrode torso tank, which records from silver-silver chloride electrodes embedded in the tank itself. Additionally, we utilize a range of recording arrays to record from the cardiac source itself, including an epicardial sock, intramural plunge needles, and, most recently, a novel pericardiac cage. The pericardiac cage is a 3D printed scaffold embedded with 256 recording electrodes. The electrodes are arranged in a closed surface around the heart, and the entire array can be lowered into the torso tank. This allows for excellent contact between the electrodes of the cage and the conductive medium within the tank, allowing for good capture of the cardiac signals. We can simultaneously record from all of these electrode arrays, achieving an unparalleled sampling of the cardiac source from multiple different locations. In order to correct for geometric errors, such as the position of the heart, again we turn to the pericardiac cage. Because it is rigidly fixed within the tank, registration of it is as easy as digitizing the locations of each of the electrodes. This is done using a mechanical digitizer. To control for errors in the signals that we acquire, we rely on good grounding practices and a custom acquisition system that allows us to record simultaneously all of our electrode signals as well as reference and ground signals.
If you're interested in hearing more about our new experimental signal acquisition system, then go check out Brian Zenger's talk at the end of this session titled High Capacity Signal Acquisition System for Flexible Simultaneous Multi-Domain Acquisition. What a mouthful.
We also rely on a range of post-processing steps including filtering, baseline correction, and fiducialization of the signals. We accomplish all of this post-processing using Pfeiffer, an open-source MATLAB package that we have developed and maintained.
In this study, we leveraged this experimental preparation to compare and contrast several common ECGI formulations.
The data for this study comes from an experimental protocol where we pace from needle electrodes embedded in the right and left ventricles. We selected two pacing locations, one in the anterior left free wall and one on the posterior left free wall. For each of these pacing locations, 40 heartbeats were isolated from a continuous recording using Pfeiffer. This made for a total of 80 heartbeats examined during this study. We then assessed ECGI reconstruction accuracy using a variety of ECGI formulations. These include boundary element method using either Tikhonov zero order, Tikhonov second order, or truncated singular value decomposition (TSVD) regularization, as well as method of fundamental solutions or MFS with Tikhonov zero order regularization. For each of the boundary element methods, the L curve was used to select lambda value. And for the MFS-based method, Cresso was used to select the lambda value. We then assessed the reconstruction of pericardiac cage potentials from the recorded body surface potentials using a variety of metrics.
Before we look at just a bunch of charts and numbers, though, let's have a look at the signals themselves.
First, in order to see what's going on better, we're going to take our pericardiac cage, cut it along one edge, and flatten it so we can see all of the electrodes at once. First, let's look at the measured electrograms from the cage. I'll play each beat twice so that you can see it. In the subsequent visualizations, I will leave the measured potentials on the top. Next, we'll look at Tikhonov's zero order with boundary element method. Now we'll look at Tikhonov's second order with boundary element method. Next is TSVD with boundary element method. And finally is method of fundamental solutions with Tikhonov's zero order. Now let's look at all four inverse reconstructions as compared to the measured. Let's stop the beat in the middle of the QRS, just about there. During this dynamic part of the heartbeat, we can inspect some of the strengths and weaknesses of the different inverse methods. For example, we can see that boundary element method Tikhonov second order and MFS Tikhonov zero order resulted in a lot of smoothing. Let's go ahead and look at some of the accuracy metrics we calculated, starting with RMSE, or root mean squared error. We'll see on this graph boundary element method Tikhonov zero order, Tikhonov second order, TSVD, and then MFS Tikhonov zero order appear from left to right. These box plots represent all 80 beats spread across the two pacing locations. As we can see, each of the inverse methods performs similarly. Next up is spatial correlation. This is the correlation between measured and reconstructed potential maps averaged across all time instances for a single beat. We can see that while all methods show quite high spatial correlation, Tikhonov's second order with boundary element method and MFS with Tikhonov zero order showed the highest. Next is temporal correlation, which is the correlation between reconstructed and measured electrograms from a single electrode averaged over all electrodes for a given beat. The correlation values we see here are rather high given the context of inverse problems, so let's take a closer look at some of the signals. Here we will look at the measured signals in black and the reconstructed signals in blue using boundary element method and Tikhonov's second order. We'll scroll through all the electrodes, and I'll go slow at first so you can see them and then speed up. Notice how the inverse reconstructed signals tend to be a little bit noisier than the measured. However, the amplitude and the morphologies match rather well. The morphology matching gives rise to the high temporal correlation that we observe. We also notice high correlation not only in the QRS region of the signal, but the T wave as well. This is notable as many inverse studies neglect the T wave. However, T wave morphology is important in certain disease contexts. After examining the metrics of spatial and temporal correlation in RMSE, we thought it would be best to also explore some metrics that capture other features of the inverse reconstructed signals. The first of those is spatial correlation of activation maps computed on both the measured and inverse reconstructed potentials. In all of these metrics, it is interesting to notice how Tikhonov's second order with boundary element method and MFS with Tikhonov's zero order perform similarly when compared to the other two methods. The next metric we examined was localization error of the earliest site of activation. Finally, we calculated the average spatial gradient of potentials at the peak of the RMS for each of the reconstructed beats. Overall, our experimental platform, and in particular our rigid pericardiac cage, has allowed us to generate a dataset in which many of the familiar sources of error are attenuated. This allows us to examine and validate various ECGI formulations in a way that has never been done before. Here we report in this study ECGI accuracy that is higher than any that we have noted in literature. While the datasets used here may not be perfectly representative of the clinical scenarios involving a moving heart and inhomogeneous torso conductivities, they do allow for a very powerful and robust platform for examining the fundamental behaviors of various ECGI formulations. For example, by assessing the four inverse methods that we showed here, we saw a striking similarity between Tikhonov's second order boundary element method and method of fundamental solutions Tikhonov's zero order. These two methods proved to be more accurate according to some of the more traditional metrics, such as spatial and temporal correlation in RMSE. However, when we examine some of our other metrics, such as localization error or average magnitude of gradients reconstructed, we can see that methods such as Tikhonov zero order or TSVD with boundary element method perform superior. These comparisons between inverse results could have implications for which one is most suitable for a given application.
I would like to take this time to thank all of my collaborators, my mentors, my PI, my funding agencies, all of the wonderful support staff at the Cardiovascular Research and Training Institute, as well as the Scientific Computing and Imaging Institute, and everyone who has helped me along the way. Science isn't a one-person job, and it takes a whole team to create results and dynamic experimental preparations like this. Thank you all for your time.